The goal today is to use an example problem that is pretty challenging problem, especially for reinforcement learning, and see how far we can get using some of the techniques in the book and some maybe extra modifications to those techniques that will help us out make progress. And all of the problems that we solve with these techniques fit this model of a problem, which is like a Markov decision process model. And this is what the book introduces at the very beginning. So the agent is the thing that we're trying to train, which is going to take actions in the environment, right? So the agent takes actions. Now, the agent has information available to it to take actions, and that is the most recent reward it's received and the current state it's in. Now, this reward signal is used in the process of training the agent, but when the system is actually deployed, the agent should be able to make a decision only based on the state. And what the environment does is it takes the action and it provides a reward and a state for this transition. So this sort of action transformed into the next step is called a transition in the parlance of reinforcement learning. And this could be, a stochastic or deterministic environment. So in general, when you have one of these environments, you generate this sort of trajectory of states, actions, and rewards. And the environment also, it's important that the way the environment dynamics work is that given a state and an action, there is some transition behavior that you expect. And that will always be the case. And it only depends on the state and the action, not any extra information. So this is what makes the process a Markov process, is that you know everything about the next step just from the current state that you're in. So if we think about, a problem like a Rubik's cube, like this it does meet this criteria, because like if we think of an action we take as maybe like just doing a rotation of the cube, all we need to know is the current state of the cube, right? Like the history of how the cube got into this particular state doesn't matter. We can, like the environment of the cube will tell us exactly how it transforms when we make an action like this. So, when if we want to use this as a model for an environment, we need to think about, the states, what they look like, and what the reward means. Like in this case, this is going to be set up more like a maze solving task, where if the cube is scrambled, like if you imagine we're in a large maze, a random part of it, and we're trying to find the exit. In this case, the exit is like the solved state. And for one of these cubes, there's only one unique solved state of the cube. So in the whole space of however this could be scrambled, we're trying to find this one special state. So, typically a problem like that would be set up where this reward signal is very sparse. Like we don't really know anything until we've solved it. Now, you can do it differently. You can try to provide more frequent reward signals, but we'll talk about that a little bit later. But there are some downsides. There can be downsides to engineering a reward signal in that way. But we can talk about that a little later. So I just wanted to introduce this the way the MDP is set up as it's defined in the book. Now we can start thinking about how we would, translate this into a reinforcement learning problem. So, first of all, like it looks like there are these colors and these different squares, but really each of these faces, like every piece of the cube, like if you think these corner pieces have like three sides to them, and actually every piece of the cube, like the edges and the corners, are completely unique pieces because they all have their own unique combination of these other colors. And actually, at a more granular level, like every single face, if we ignore the fact that these three faces are connected, if we just look at every face and we orient the cube so that the center pieces are in the same orientation, Like really, you can think of every rotation as being done around the this central axis of the cube. Then you have what ends up being 48 unique, facets to the cube, you could call it, or facelet, where a facelet is like a single color face. And it's true that in a solved cube, we have like the front side is all white, the top side is all green, etc. And you can encode it that way, but actually every single facelet is a completely unique piece, right? Because like even though like these are both white faces, this white face is a corner piece with these other two colors, and this is an edge piece. So if we want to be like the most general that we could possibly be about defining the state of the cube, we can, just make this list of like 48 distinct indices. And like the reason why it's 48 is because I'm ignoring the center piece, right? So there's 9 facelets to a face, but we don't have to worry about the center one because we're assuming the center one is just fixed in place. So we only have to worry about the 8 others, right? And there's 6 faces, 8 facelets to a face. So we have this, 48. So you can think of this as like in a solved cube. If I go and I have to define like an order in which I'm numbering the faces. So I'm going to just arbitrarily pick this ordering where I start at the top left corner and I sort of count this way. And then I also have to figure out, like how I start counting the top face. So I'm just going to use the convention that if I'm just going to rotate like whatever face I care about into this front position and then count it in the same way that I counted the front face, right? So that way I can take this list of 48 and I have this ordering of the faces. So I'm just defining like a lexicographic ordering for all the faces of the cube. Okay, so then if I just take this list of 48 and I reshape it where this is now an 8x6 matrix where now each row each column represents one of the 6 faces of the cube. And these also, what I'm showing here are the colors. So like this is, one represents white. Actually, do I have the colors? Yeah. So I have this, like, this is what the colors are. So the index of this vector is like what it means. So 1 is white, 2 is green, etc. And then these are the solved cube values. So this is like if you want to actually render the cube. I know for like these are what the values should be when the cube is solved, and these are what the indices should be. So this is like every square, every facelet is in its proper place in this, right? All 48. So now, if you think about like a cube that's scrambled, what we can do is we can write it out in the same way, and we would just permute these indices around. So like instead of in position 1, it should have facelet 1. But if we do some kind of rotation of the cube, then some of these indices are going to swap positions. And that will define how, this is short of a solved cube. Because a solved cube, if we look at all the indices, the index should match the value of the index. The reason why these numbers, I'm using unsigned 8-bit integers here just because I don't need values higher than 48. And this makes, if I end up generating a lot of these cubes, it's better for storage if I don't use as many bits. Also, someone asked what browser I'm using. Oh, this is just Florp, which is a build of Firefox, I think from Japan. But it has these nice formatting things or side tab stuff. Okay, so are there any questions about how I'm like, numbering the cube and like defining a solved one? Going through the indices. Okay. Great. So now the next step is to figure out like the action space and how the moves work. So we're going to have to come up with a way of representing how a particular move transforms these indices. So to do this, I'm going to consider um, moves that are very simple. So instead of like you could think of combinations of moves, but because the cube, I'm always defining it so it's always oriented in the same way. So like this white center square will always be forward, and same with like this one will be to the left, this will be to the right. So I'm only going to consider um 12 total moves that can be made. And those just correspond to selecting a face, like in this case, the front face, and rotating it either clockwise or counterclockwise, right? So then everything you do to the cube can be represented as a move like that. So for example, like rotating the center like this, like is not a move because all I did there is I changed the orientation of the cube and then I made two rotations of the top and bottom face. So that would end up being represented by like two different of these more atomic moves you could say. But these are like the most basic moves that you could define. So I'm just going to define this type hierarchy on the moves because it's convenient to just have these faces and then these directions where there's like two directions, clockwise and counterclockwise, and there are 6 faces. So that makes a total of 12 moves. And the nice thing about this is we can always reverse a move. Like here, I can define this operation where if I have a move on a particular face, clockwise, that move will always be reversed by just doing it counterclockwise. And vice versa, if you have a counterclockwise move, you can always reverse it by doing it clockwise. So then we have to look at how the squares are permuted, but by a move. So I have that defined here. And I said, remember, like each face has these 8, like numbered 1 to 8, ignoring the center square. So the first thing you have to do is for the facelets that are actually on the face that you're rotating, that's always going to be the same transformation where you do this rotation, right? And you end up moving all of these around and permuting them. So I'm going to transform them into the 48 sort of based index later. But for now, I'm just going to consider 1 to 8. So here, this is the clockwise permutation of the face. So what this means is that 6 goes to, or sorry, 1 goes to 3. Yeah, sorry. So you see how 1 is in the 3rd position of this vector, right? And that's because when I do this clockwise rotation, right, this is in the 1 position, and then it ends up in the 3 position, right, as I count across it. So that's what this clockwise permutation vector defines. And then the more complicated part is figuring out how all the off base squares get transformed, right? Because also all of these other, right, we have like 12 other facelets that get moved when we do this rotation. And these all, I've written this in a very compact way so that it's just like, it's easier to process later. But what this means, I have it written out here, is that if the front face is rotated, and this is all clockwise, because the way I've written it out here is I can always just apply this in reverse to do the counterclockwise rotation. So if the front face is rotated clockwise, then the squares on the top face, which is 2, right? Because I have, this is the face ordering, right? Top is 2. The squares on the top face in position 6, 7, and 8 will be mapped to face 3, which is the right face, in positions 1, 4, and 6. So this is just written in this order. And yeah, as long as you go through the cube and you first apply this permutation and then these these permutations, then you get a complete reordering of the cube for every move that that you make. And then because I'm going to be doing this a lot, this function just ends up calculating all of this as a lookup table that I can reference later. So there's 12 moves, right? The 6 faces and the 2 directions. And what's being shown here is this is the total permutation for each of the 12 moves. So basically, if I take the cube I have and then I reorder it according to this vector, then that will be the effect of applying move 1, where I have the moves numbered. Where do I have them? Yeah, so here are the moves, right? So I have this vector of 12 moves. So the moves are just, I can just reference them by a number from 1 to 12, or 1 is front clockwise, 2 is front counterclockwise, and so on, bottom counterclockwise. So see the moves here. And then this rotation lookup just allows me to, first pick a move, find its index in the list of 12, and then just grab this permutation of the facelets. So I'm just reducing the entire cube transformation into a lookup. And the result now is I can make these functions that rotate the cube. So here, just like to do a sanity check that this is working properly. This is starting from a solved cube, and I rotate the front face clockwise, and then I can rotate it counterclockwise. And this is just showing with the ordering convention I already set up what the rotated cube should look like if I actually, then color it. Yeah, this is, oh yeah, no, forget about, yeah, this doesn't matter. So yeah, and then I can see, this is just through these selectors, I can select any of the 12 moves, and this is just showing how it transforms the cube. And, if you grab one, you can just verify that this is doing the correct transformation. But yeah, all it's doing to do this, right, is like, this is the part where it's just taking like a new cube, which is just a vector of these 8-bit integers. And then, yeah, it's just taking whatever cube we're starting with and resampling it according to the indices in the rotation lookup. So this makes sense to everyone?
Yes.
Good. Okay, cool. So there are no questions about the rotations. Okay. So let's now move on to actually defining this as an MDP problem, which is the thing I showed earlier from the textbook with the agent environment interface. Now, I mentioned already, you could just treat this as a problem where you get a reward for solving the cube. And that is sort of eventually what I end up doing. You could also think of having a more dense reward function where you try to score it. So in this case, this scoring function is checking to see how many of the 48 indices match the solved cube, right? So there's like a percentage. So you can basically give it a percentage score, or, a score from 0 to 48, where 48 would be, all the pieces are in the right position. 0 would be nothing is in the right position. And then when you do moves, you could generate a reward signal, which is a measure of, how much the score changes, either up or down. And it's true that, like, if you start with a scrambled cube, the only way to get the maximum score in that case is if you solve it completely, right? Because that's the only way to, like, the maximum score is 48 or something, whatever you start with. So, but we would still have to do it as like a discounted problem, because that doesn't encourage it to solve the cube quickly. Just like if we give a reward of 1, it's just like the maze solving task. If we give a reward of 1, we have to treat it as a discounted problem, so that the reward is lower if we spend more turns trying to find the exit. The other approach is to give a reward of -1 per step, just until the cube is solved. And that way, like if we compute the value of a state, or like a state is just a particular configuration of the cube, then if that value is accurate, it should be like, let's say -10 would mean that it's 10 moves away from being solved under whatever, policy that we've currently trained. So that way we could treat it as an undiscounted problem. And so, this is like one example of a scoring function. You could do other scoring functions that try to inject some kind of domain knowledge into the problem, like maybe if a particular group of these indices is solved, then those are more important than others, and you can give a higher score for that. So you can start like trying to engineer these scoring functions, but there is a problem with this, or there can be a problem with this, which we sort of went over looking at the book, where there's this comment in the book that it's better if you keep the reward signal as basic as possible. Like if it's possible to solve the problem in that way, that's better than trying to coax the agent into behavior that you think might be good. So I don't know if anyone's run into this in trying to solve problems, but does anyone have any intuition of why like it might be a bad idea to try to create a more dense reward function where we give it a reward based on the percentage of the cube that's solved? Yep. Evelyn?
So we want to encourage solutions which may pass through areas which are of lower reward. And so we want to give a signal which is not too dense in order to avoid that.
Yeah. I mean, if we have in fact solved the problem, the value function we learned should account for all future rewards, which would include the ones where we dip down and then go up again. But it may make learning that much more difficult. I mean, really what we care about is solving the cube. So it's possible that, like, let's say you didn't know anything about this problem. It's possible that there are states where it appears as though a very high percentage of the cube is solved, which would produce a high score according to this metric. But that may actually be further away from a solution than a state that, superficially looks more scrambled. And if we actually make a scoring function which is based on some complicated analysis of the cube, I mean, at that point we're just using someone else's, solution, or like what they know about solving this. It's not a general solution. So you have this problem that, your scoring function may give a false representation of how close you are to a solution. And it may mislead your technique somehow. But who knows? Like you have to sort of start solving the problem to see if that's an issue. Um, it often when you have problems with really long time horizons and it's too difficult to, wait for a reward signal, that you feel like you have to sort of give intermediate rewards where it's like, this is some kind of milestone towards reaching the solution. And by setting this reward function, I'm telling the problem that having a higher percentage of these squares in the right place is some sort of important milestone. And it may in fact be a problem where the cube looks completely scrambled until like right before it's solved, in which case you are making significant progress in the solution, even though according to this score, it doesn't look like anything. If you leave a super sparse reward signal where you only get a reward for solving the cube, then the agent will have to figure out on its own the importance of all the intermediate states. Like only and that it's sort of like solving the maze where you rely on the information about where the exit is to filter back through all of the previous states in some efficient way. But actually, another maze analogy to this is if you think about having a very large maze, and let's say you could actually measure your distance to the exit, like if you just drew a straight line, you could imagine that there are states that could be right by the exit, but actually the furthest away from the exit in terms of traversing the maze. Like a maze could certainly be designed that way. And then you definitely wouldn't want to provide a reward signal for, it's true that once you actually get to the exit, your distance is zero. But that doesn't mean that a short distance is actually close to the exit, like in a real sense of how you solve the problem. Um, yeah. Someone had I don't yeah, there is if there's an analogy to overfitting when you have a nonlinear solution. I mean it is sort of like that in the sense that um like when you overfit, you're placing too much importance on a few examples that don't necessarily generalize. And in this case, we'd be placing too much importance on how we've selected this scoring function. So anyway, there I can have a version of it with this score. I can also have a version that just gives a reward of -1, or in this case, yeah, I'm gonna later make that. But we can try different versions of it. But the most basic version we're gonna work with is to give a reward of 1 for solving the cube, and then treat it as a discounted problem. And another reason for doing that is we don't want the values to get too crazy. Like if we give a reward of -1, where then the solution is like how many steps we are away, we're going to have a big range of values, which depending on the type of function approximation we use, that could be really bad for the function to have to deal with like these large range of values. Whereas if we do it as a discounted problem with a reward of 1, then um we're going to have values that basically range from 1 to 0, where like 0 means we're as infinitely far away from the solution, and 1 means we're one step away, or right at the solution. So it provides a little easier time for the function approximation. So anyway, once I have this step or this way to do the transition where I use the rotate cube function, and then I can choose what kind of reward signal to give. Um, then I can finish defining the MDP, which in this case I have to have an initialization function, which in this case I have a generic one where I just give it a number of actions. And this is like when you start a problem, where this is an episodic problem, this is like how many scrambling moves do you want to use to make the cube. So this is showing like 5. Right. If we do like 0 scrambling moves, obviously like the cube is just solved here. And then if we do 10, it looks way more scrambled. So here I am showing this score function here, where this is just the number of faces that are in the right position. And if I do this, like in general, like the score is not going to be 0, because even with a maximally scrambled cube, you just by chance have some of these. And that's actually another indication of what a problem might be with this scoring function, right? So I just scrambled this cube with 40 moves, which is, really scrambled. And we can see that, we have a score of like 2, or okay, so that's a score of 0. But here, we end up with a score of 6 with this. And then if I scramble it just, 20, I got one that was like a score of 0. So this doesn't necessarily correspond to how close we are to the solution. Now, if I make one of these MDPs, this is just a matter of, I have this function to create one. I just need to provide a list of the actions, which here are just the basic atomic moves, the transition function, and then the initialization function. And then this is to check if the episode is terminated, right? So this means like, is the cube we have the solved one? And if we have the solved cube, then the episode can be over. So we can see this. I'm like running an episode where we just start with some amount of scramble and then we proceed. So this is what it'll look like where we get a sequence of these cubes. Where here, this is just the random policy here, manipulating the cube. Now I have cut this off here. And the reason I've cut it off is because if I don't cut this off, in general, this will just go on forever, right? Because the chance of just stumbling upon a solved cube, if we start with the scrambled one, is really practically zero. And that's one of the reasons that makes this problem much harder than like a typical maze problem. So if we go back, if we look at some of the examples earlier in the book, like some of the grid world examples, actually, do they have? I guess there was a grid world. Where was? But when we have these grid world examples, I mean, this is like a really easy one. But let's say this was a more elaborate maze problem. When we go about solving this, either we can see all of it at once or we can't, and the problem's too big. And then there is some reliance on randomly stumbling upon the exit and then slowly building up information from there. And the problem here is that, if I just let this run for like 100 steps, um, you know, we'll see. Oh yeah, sorry, this is like showing it in this form. But yeah, this is showing all the cubes. And we can see like it's going 100 steps. I could make this, a million, 10 million, 100 million steps, and it will just keep going and never actually reach the terminal state. And that is a problem because if I have the reward signal like as it's sparse, then we'll never get a reward signal and we won't know anything. There is some hope maybe if we try to use the scoring function that we would learn how to get, higher scores, but it's unclear how useful that will be. So anyway, this cube is actually a deterministic problem, right? Like if I make a move, we know exactly what state we end up in. And it turns out like if that's true, we can make some of the techniques a little bit easier. And that's what here I'm defining a cube that the difference here in the previous one is that I'm telling the solution techniques that this is a problem where I actually fully know the distribution of the transition. In this case, it's not really a distribution. This is the probability of this transition happening. And the probability is just one. So when I make a move, there's only one cube that it ends up in. So this is useful if I know if the problem has this deterministic output, because it means that if I'm considering like doing an action, like one of these rotations, I don't actually need a function that has an idea of how good this action is, where there's 12 of them in this case. Instead, I can just look forward at the state I end up in and just care about how good the states are themselves. And this is an important concept from the book, and you see it play out in this value iteration algorithm where or actually sorry, here, where if we just have state values, which we're going to try to do this where we only have state values, then we can actually check all of the action values, which tells us how useful each action is, just by looking forward from the state values. So this is saying like S prime, these are transition states that we end up in. And in the case of our Q problem, even though we have this whole probability function, really we're only going to have to consider one transition state into the future. And this makes it a lot easier, and it actually allows us to do techniques that aren't quite value iteration like we looked at with tabular problems, but are more going in that direction than the action value methods that we often see when we have solutions with approximation. So this is just defines the cube as where I'm telling problem it's a deterministic environment. The other thing I'm doing here, which so I already mentioned, there's going to be a major problem with this, especially here. You can see with the reward function, right? I'm calculating the reward here, which is if the cube is solved, then you get a reward of 1, and otherwise the reward of 0. So if I just initialize a state, even if it's kind of close to the solution, this algorithm is going to have to explore randomly with it. And it's very likely it will explore randomly and go away from the solution, even if I start close to it. And at that point, it hasn't learned much yet, and it will keep randomly exploring. And if my termination condition, like I had earlier, was that the cube is solved, then this episode will never terminate. So we don't need the episode to terminate if we do something like temporal difference learning, because we can try to learn on every step. However, if the cube is just randomly exploring in states that are far away from the solution, it's likely it'll just never reach a solution. It will never learn anything. And like the process just is just going to be really, really inefficient. So there is something we can do to design the problem so that we have a better chance of learning in a more incremental fashion. And what I've done here is I've created a different termination check. And there's a little bit you can, play around with this a little bit. But so if the cube is solved, then we've terminated. So that's fine. We'll leave that the same. What I'm gonna add to the state information a little bit. And the information I've added here is when I initialize a problem, first I initialize the cube, however many moves I'm scrambling it. Now I'm gonna save that as part of the state. So if I look at the state, I know when this episode started, how many moves did it start out? And I'm also going to save the move count, which is how many moves it's gone so far. Now, these two pieces of information, if I use an approximation function, these pieces of information will not be available to the approximation function. So which is it's as if they don't exist in the state, but I'm only going to use it for the purpose of terminating the episode early. Now, if you take this cube and scramble it a certain number of moves, we know that if we have the optimal solution, like if we can solve the cube perfectly, then we shouldn't need more than the number of scramble moves to actually solve it. So that is like that you can just deduce logically. And of course, that's only if we have the perfect solution. We may need more moves than that. So what I've done here is just arbitrarily said, if the move count is greater than 2 times the original number of scramble moves, then I'm just going to consider this episode as a lost cause. And, you get there will be no reward for this episode. And it will allow the problem to reset again into a state. And as long as some of the time we find a solved cube, then this will save us by allowing the problem to reset. Now, if we run this algorithm and we see that, we're solving it like 1% of the time, then that's really inefficient. So another thing we can control is how much we scramble the cube initially. And right, if we do that very little initially, then we will effectively limit the length of an episode because we won't allow it to run longer than that. So we don't have to start out with a fully scrambled cube. We can make the problem a little bit easier. And then, but this is important because otherwise, without this information, you would have no way of knowing when to reset a problem. And this also keeps in mind the fact that we know the optimal solution should at least, we'll definitely be able to solve the cube in fewer than this many moves. The reason why I have this 50 here is also because, if you know about these cubes, even if you scramble it like 100 moves, once you reach like 20 or 30 scramble moves, it's sort of maximally scrambled. So you don't actually have to multiply this by 2 of that. Like, even something that is far from an optimal solution should still be able to solve it in 50 moves. Yeah. So this is one approach that hopefully allows us to not just wander around in bad states indefinitely without any reward information. Are there any questions about this or how, you know, I've added these sort of two other things to the termination condition. Originally, it was just this checking that the cube was solved.
Mm. Well, I don't have any questions, regarding the condition about the move count being, having a heuristic about how the well, a heuristic of how many moves there would be before the episode terminates based on the heuristic of being 2 times the number of scramble moves.
Hmm.
And then the condition about how many iterations to scramble during episode initialization.
Hmm. Yeah. So also when I set up one of these problems, I can also, the way this is set up is you can either pick a range of scramble moves that will occur every time an episode is initialized. So here it's just randomly selecting from across this range. But if you set these as the same value, then it will always scramble the same amount. So setting at 50. I mean, the 50 is just because if someone decided to scramble at like 100 moves, you don't want to check 200 moves for the solution because scrambling at 200 moves is really no harder than scrambling at 30 moves. It's not actually we are at that point we're going to be fully in sort of this dark forest of having no idea where we are in the cube states. I mean, we very quickly start getting into that range. But actually, before going into the approximation solutions, um, there is we can take a different approach to solving a more limited version of the problem. And the advantage of this approach is that it'll give us some kind of exact solution, which is these tabular solutions that we had where we can use the techniques from the first part of the book. And we already know that the number of cube states is really big. It's about 43 quintillion. People have calculated it, and you can get, some. This is more of an exact number, but if you just try to get an upper bound, it would be even higher than this. But you can tell that whatever it is, plus or minus a few orders of magnitude, it's well outside the range of feasibility. But we could consider cubes that are closer to the solution as a way to just see what kind of progress we can make, what the problem looks like, how hard is it to solve. And we know that, we have this one unique solved cube. And then there's, 12 moves we can make from the solved cube. And those 12 moves will produce 12 unique cubes. And we know that those are each one step away from being solved. And we can go on from that. We can keep branching. And we can, every time we branch, we multiply the state space by 12 in the worst case scenario. It's not actually that bad because we end up repeating states sometimes when we do this. So the factor will be a little less than 12, but you can take it as an order of magnitude of like 10 or something. So every, additional step in the sequence we go forward, we, maybe 10x or 12x our state space. So by doing this, though, we know that, let's say we choose a number n and we, expand the space of cubes by n by, keep branching, and we basically branch out to a depth of n. Now we know that every cube in that space is at most n steps away from being solved, right? Like we know that because at a minimum, we could just reverse the moves that we had made. And in reality, some of them will be shorter than that. So we can generate all this, and we only care about optimal solutions. So of course, like if you look at all those cubes in that branching, and we're trying to look at like, well, what happens if we make a particular move? There are going to be moves that will produce cubes that don't exist in that space. But those cubes don't matter at all because we already know that they are further away from the solution than the states that are contained within the space. So we can just handle those states in a particular way. And like one option is, because this is a tabular problem with an exact solution, we can actually do the like -1 per step reward signal. So we know that the worst possible value for the optimal solution is -n, where n is the the depth that we've gone in the branching. So as long as whenever we make a move that would produce a state which is outside of that space, we can just assign that. We can just terminate the problem. Like say that's a terminal state, just a generic terminal state. We don't care what the cube is, and we can just assign a reward which would be a worse value than any reward that we would ever get for one of the real states. Right? It's like let's say we gave a reward of like -n for that transition. Then we won't actually modify the optimal solution, right? Because any transition that would produce a reward of -n will never happen under the optimal solution because that will be a lower reward than anything that we could get otherwise. So we can try to set this up where we create a state space, which is right all cubes that are at most n moves away from a solution. Here we can do -1 per step unless we exit the state space, in which case we'll handle that by giving a worse negative reward. And then for the terminal state, we have the solved cube, which will terminate and just have a reward of -1. And then if we ever exit the state space, then we just give this a really bad negative reward. So we terminate and we make sure that that is always penalized enough to make it like it's never the right option to do that. So here I have the purpose of these functions is just to accumulate this list of states and do it as a set. So in a set, all the elements are unique. So this ensures that we're not going to duplicate any states. And we can see this is just an example of we start with the solved cube. And then this is, these are the 12 cubes we end up with from just that one move scramble. And then this is actually showing, sorry, this is also including the solved state here. But this is actually showing all of the cubes that are within 2 moves of being solved. And then I'm not going to show more because obviously the space is getting big pretty fast. Now, once we construct this state space, the purpose now is to turn it into this tabular problem where we have a transition map. This is a deterministic problem. So every transition only has a single transition state here. The transition map I build up is just a matrix. It's just a 12 by n matrix where 12 is the number of moves, n is the number of states, and each element in the matrix will show, actually you can see it here in the one that I've already constructed. So I have to pick an n, right? So this is showing for 7. So if I construct this problem where I go at most to 7 scrambles, this is showing the state transition map. So it's showing for every state in the state space, right? Here's the list of all states. There happen to be 9.2 million states here. And then this is showing for every state and every action, what is the state you end up in? And the reward transition map, all these -1s you see are for all the normal transitions. The -9 is that's the reward for like a bad transition. And you can see here it matches up with this index here. This is the index of the terminal state, right? So this is just showing how all of these actions, like from this state, all of these actions, well, except for this one, right? So you can see here in the reward transition map, how if you're in this state and you look at all these other actions, all of these actions take you to the terminal state in a bad way, like not the solved state, but where we're sort of making an illegal, in the context of this problem, it's sort of like an illegal move. And these all have a reward of -9. And then the one action that actually makes progress towards a solution gets a reward of -1. So yeah, when you have one of these tabular problems, you generally have this finite state space, this finite action space, and then these transition maps. Or like, if you see it in another context, it would be like a Markov matrix that shows you how all the transitions work. Yeah, and then the terminal states, this is just a bit vector, but you can see here, there's only a single terminal state index here, which is this one. Yeah, okay, so any questions about how setting this up as a tabular problem? Yeah, 9. Yeah, so we could make this bigger. We could go to 8, probably 8 in terms of scaling. This starts to become impractical once we get probably to 9, where the state space size is just too big. So we can see for 7, we only have 9 million states, right? I'm just running this on a regular desktop computer. Oh, the other thing that we can do, which might be kind of interesting, is to see if we scramble. So what this is showing is if we just take a cube and we scramble it n times, what percent of the time is that cube in this state space of 7? So this is just like, just because you scramble a cube more times doesn't mean you're hopeless. Like we can see here that about 24% of the time, even if we scrambled the cube 10 times, we would still end up with 1 within 7 of being solved. And you can see it's only when we get, here to like 18 that we're now less than 1%. And there's some like even odd weirdness that happens where even moves seem worse than odd moves for being solvable. And that has to do somewhat with how moves get reversed from the solved cube. But yeah, so these are just some statistics of, for later on, if we're trying to look at an approximation solution and see like, even if we had something that really realistically can only solve simpler cubes, we would still expect it to find the solution like half the time if we're looking at 8 move scrambles. So the nice thing about setting up the problem like this, if we just want to get, we want to make it's helpful sometimes with these problems to do something where you actually get an exact solution, because the other techniques involve sampling, learning rates, convergence issues, lots of things that could go wrong. So once we set this problem up, like I have up there, we can use value iteration, which is this technique right in the book here, where we just have a state value function and we update it with this update rule, where we're using the Bellman optimality equation to update it. And if we do that, we can see that within about 50 seconds, we get an exact solution for this more limited problem. And what this solution tells us is for all 9.2 million states, exactly how far away we are from a solution. You can see most of them are -7 because a lot of the 7 scrambles are 7 steps away from being solved. And also, this only took 9, yeah, 9 sweeps through the state space. And then we also have the optimal policy, which here is totally deterministic, but it tells us for any of these 9.2 million states we're in, exactly what move we should make for the optimal solution. And we can see what that looks like here, where like here's an example of the policy at work, where we start with this cube here. I'm just like initializing it. So this is a cube, it's been scrambled 7 times. This is what it looks like. And then these are the steps towards solving it. So here it can be solved in just 3 or 4 moves here. The final move is omitted here, but the final move is what is just the solved. It just makes this a solved cube. And we can see if we just initialize this a few times, this value here will tell us, it'll match how many moves it actually takes to solve this, right? So oftentimes we get 7, but here, we get -5 because this happens to be only 5 moves away from getting solved. So what I'm showing here is an exact solution. Now, in order to do this for the larger state space, right? Like the whole problem with why we can't apply this technique for a larger state space is because like we're already at 9.2 million states. We're gonna, this is gonna very quickly become, too big to fit into memory. Plus, it's gonna take, this solution time is gonna also scale badly with like this is gonna take 10 times longer or more than that to solve. So we're gonna have to look at some approximation techniques. And there's a question about can you apply so transformers, are just nonlinear approximation functions which work on sequence data. You could certainly formulate a feature vector. Well, we'll talk about feature vectors in a second, but you have to transform one of these cubes here. So here in the tabular problem, each cube is just uniquely identified by its index in the state space. When we use approximation techniques, we're going to actually take the cube itself and turn it into some kind of vector. It could be a vector of symbols that you could pass to a transformer. It could be a one-hot encoded vector that is just all passed to one big approximation function. But it doesn't matter if it's a transformer or a fully connected network or just a linear function. The job of that function is to estimate these values that we have here. Where here we have the exact value of every state. And when we use something like a transformer or another type of neural network, we have a function which, if we pass it a state, it gives us one of these value approximations. And the success of the technique will entirely depend on how good that function is at generalizing in a way that's useful for states, because it can never see all the states. It can only see some of them. And we hope that when we present it with learning information of particular states, it learns some kind of useful pattern about what the states look like. So it can still infer what the value should be of other states. I mean, all these approximation techniques, we need some kind of interpolation success for them to work. But before we get into that, oh yeah, so the other thing is once we have the solution, right, we can actually look at, so what this is showing is for all of the states, how many of them are this many steps away from the solution, right? So obviously we already know there's 12 states that are 1 move away, and then 114 that are 2 moves away, and then 1068 that are 3 moves away. And then, this is growing. We can see it's not growing, like the ratio is not 12. So this is showing the ratio of the number of states n moves away divided by the number of states n minus 1 moves away from a solution. So The only time we scale up by 12 is for the first step here, right? Where we go from the exact solution to the 12 states that are one move away. And we can see for every other step up, we only need to consider about, nine and a third additional, like as a multiplicative factor, about nine and a third times as many states. But we can get some idea, right? Like we know in general, maybe we have to, if we consider like 20 or something, how this is gonna, I mean, we already know it's like 43 quintillion total cubes available, but even if you just think of the number of cubes that are, 10 moves away from being solved, we're gonna, if we keep scaling this up by 9.3 or so, it's gonna get very large. But okay, so we have this. We also, now in the future, when we explore the state space, like let's say with another technique, this does help a little bit because we don't necessarily need to find this one solved cube. We actually just have to find one of these, 9 million. I mean, it actually doesn't end up helping. It depends on how good our approximation function is, but it may have an easy time getting maybe this close to a solution. But on the other hand, if it actually gets this close to a solution, it's likely that it also knows how to get the rest of the way there. So this, you could also do this for 8 maybe, but here I stopped at 7 just for practicality. So are there any questions about this tabular solution? Or, how useful it may be? Okay. So like I said, if we want to do approximation, we have to think about how to represent the states in some other way. We can look at, if we look actually in the book here, when we first start talking about approximation methods, this is an example of one of the simple problems that we looked at. This is a very simple problem. The exact solution is this straight line here. And this is not a neural network or anything fancy, but the idea is the same, where we have this approximation solution, and the approximation solution is just an estimate. So here it's like grouping states together, and the best we can do is if we have a state in this range, we can spit out a value like this. And we can see that because of the shape of this value function, where it's a straight line, this approximation function is learning something useful, because this straight line is grouping states in a close region to what the value should be. Like it's not, I mean, this may be an easy function to learn, but this is doing some kind of successful interpolation, like modestly successful. And if we used a linear function here where it was actually, we could actually learn more of a straight line representation of this, it would happen to fit the value function very well. So this is the kind of interpolation that we hope for, where we have this large state space. We only really, we can only really check our function at particular values. Like here, if we check this value, it happens to be the correct value. And we hope that if we deviate away from this, that somehow the states that are sort of close appear to be close together from the perspective of the value function are actually like legitimately close together in value. We don't really have control over that, but we hope that if we use like a neural network technique, for example, those often can be good at generalization if we set up, the feature vector in an appropriate way. So you can go back here and think about ways to represent feature vector. The most basic way to do this is just to make a big one-hot vector where we take you know, we have the cube represented as a list of 48 values that range in size from 1 to 48. If we can just take each of those, expand them out to a 48 length bit vector, assign a value of 1, right, at the value where it should be, at the index where it should be. And in that way, we can represent to the function where all the indices are, right? Because each value, like, we don't want to actually use the numbers 1 to 48 because their magnitude is not relevant. It's just a label for the face. So, this is really sparse, and actually it is much more sparse than it needs to be. One of the reasons is that we don't actually need to fully define all 48 of these faces. Some of them end up being implied from the others. And there's certainly other ways to make this a more compact representation. But let's say we use like linear approximation. If we use linear approximation, then the number of parameters in our function actually match the length of the feature vector. And whatever we do, it's going to be way less than the number of states. But it might help if the feature vector is bigger. And when we do approximation like this, it's not necessarily the time to worry about shrinking the size of the feature vector, because we kind of want to allow as much, like, if information needs to be compressed, we hope the approximation function can do that on its own. But if we construct the feature vector like this, it ends up being, well, 2,304 bits long. However, only 48 of them are going to be turned on at any given moment. And that's what's being shown here, where this is showing, like, if we start with a solved cube at the bottom here, and the vertical axis is the rotations, and these are just random rotations, but the black values are just 0, white is 1. And this is just visually showing how the feature vector gets transformed as we go through these rotations of the problem. But we end up just moving around where these indices are 1. And of course, like, not all of these feature vectors are even going to exist. Like, there's only certain things that will appear that are just allowed by the mechanics of the cube. So we could try to remove that from the feature vector, like remove that information, but we can also let the approximation function just try to learn like what those relationships are from the really sparse feature vector. But yeah, I mean, there's some information here about compressing it. Like, this is a much shorter one. It's only 960 long. This just removes from the feature vector all of the redundant faces that are implied by the other ones. But it will end up making the space smaller for approximation. That's like, these are essential indices. This is like, actually, these are the only indices we really need to define the cube. And then there's some other alternatives that you could consider. But for now, we'll just think of it this way, where we have it as sparse as possible. But it's basically just a one-hot vector. So any questions about feature vector? So, this is what we're going to end up passing into the approximation functions, which we can, start looking at that. And hold on, I have to organize myself a little bit to see where I want to actually start going through this. And it might be, let me see if, okay, fine. So we can start here. So, one of the techniques, so actually there's this technique, if you look at the YouTube videos, it would be in part 2 of the book, the section on eligibility. This chapter on eligibility traces, this finishes all the the value and action value based approaches to solving these problems with approximation techniques. And the nice thing about it is, we had the SARSA technique before, which also, you can do this, Q learning is an extension of SARSA. But this SARSA lambda technique is just a generalization of SARSA that allows us to check the usefulness of accumulating additional rewards into the future. It's sort of like a version of n-step techniques where we don't just do temporal difference learning. It's just a superset of the original SARSA techniques. So typically when we do SARSA, being shown here, we are trying to have a function. This is showing it for linear approximation. But this linear function here, Q hat, the idea is that this function will give an approximation for all of the action values in the problem. So if we have a state and we generate a distinct value estimate for all of the actions. And the reason we do that is so that we can do this policy improvement step where we choose, the greedy action. Now, because the problem is deterministic, like I said, like we know that these transitions, when they occur, there's only one transition. If we go back right to the first part of the book, we know that even if we just have the state value function, or in this case, an approximation of the state value function, we can try to compute this argmax, where now this v would be replaced with whatever our approximation function is. And the advantage of doing it this way is that we have our function can be a lot simpler. We don't have to compute estimates for all of the action values. We can just worry about state values. And if you look at my notes from some of the other chapters, when you apply the simplified technique to the problem, it ends up making the results a lot easier to come by in a lot of the problems. So it depends, like oftentimes we need action values because the problem is inherently stochastic and we just don't know the information. We have to take samples. But the Rubik's Cube is a perfect example of applying this sort of deterministic look forward for the argmax, where here we're going to be looking at the argmax of our value approximation function. So, right in the book, notice how it said it was like the SARSA lambda algorithm for control or finding optimal policies. So here I am using what I'm calling this sort of DP lambda algorithm, or DP sort of stands for dynamic programming, but the style of update occurring in here, it's making use of the Bellman equation relationship. And then because the cube we're dealing with is, do I have it? Yeah, this MDP, like this cube environment that I'm making is the one where I showed earlier is a deterministic environment. So this technique can be applied to that. And then we can see what kind of progress we can make, testing out this algorithm and how long it takes to run. So the way I've set this up is I can create an environment, right, where I can control the scramble moves, like how many there are, how hard the problem is, and that also controls when the episode gives up. So it'll reset if it feels like, if it's exceeded the number of moves it should have taken to solve it. So, right, we know that this is using linear approximation, and it's using this this feature vector that I said is the one that's like 2,304 features long, or that's like the maximum index of a feature. Only 48 of them will be active at once. Luckily, there's sort of a sparse representation of it that makes the computation go a lot faster. So this is showing the result of applying. Oh yeah. So this problem is also the one where you get a reward of 1 for solving the cube. So this has to be a discounted problem. This value of 0.9, this is the discount rate I'm using. This is the value of lambda. If I set lambda to 0, this effectively becomes just a straight temporal difference method. There's no, eligibility trace being used in that case. And this 3 and 3 means I'm just testing this learning process where I'm only scrambling the cube 3 times at most. So every time it starts, it just randomly, and then this is running for 100,000 steps. This is the learning rate. The exploration parameter in this case doesn't have to be very large because just the nature of the problem, it's going to end up making a lot of random moves anyway. And yeah, it's not, this problem has no risk of getting stuck like in a local minimum, because honestly, like if we can find any solution at all, that's really good. So we don't have to worry about getting stuck in like a suboptimal solution, because like the risk here is going to be not finding any solution. So what this is showing is if we just scramble this 3 times, this is learning rate, and we see that it is in fact learning how to solve this. These are some statistics on the solution. So granted, this is not the most difficult problem, but the goal of setting up the problem this way is to try to incrementally increase the difficulty and see if we can approach a solution without just tackling the full problem from the beginning with its maximum difficulty. So this is showing is that we start with 3. This is learning a pretty high success rate of a solution. It's 95%, give or take. Luckily, if we look down when we only scramble the cube 1 or 2 times, luckily we have 100% solve rate. And then even though we haven't done any learning on, let's say, like 4 scrambles, we still have a somewhat high success rate there. Part of this is just probably that a lot of the states that are scrambled 4 times are still actually within this range. But even if we go a little higher up, this is still a much higher success rate than we'd expect if we just make completely random moves. So this is just linear approximation. So right, there's only like 2,000 or so parameters here. Now, what we can do is we can do a parameter study on this where we look at the lambda solution technique. And the goal here is to see like, how should we be training this? Like, what kind of learning rate? Is there any value in having a non-zero value of lambda here? So what this is showing here is this is just repeating the training for a bunch of trials. The nice thing about the linear method is it's fast enough. We can do a lot of checking here. So here, these curves represent the success rate over the first 10,000 steps. This training was over 100,000 steps, actually. So here, we're only looking at this first part of the training curve. And, varying a bunch of stuff here. So it seems like if we make, when lambda gets large, like 0.99, this is getting closer to Monte Carlo sampling, where we're just looking at the value, that one reward value we get all the way in the future. If lambda is 0, then we're actually learning from all of the bootstrap value approximation. So we're sort of ensuring self-consistency of the value function when it's this, and the information from the solve state will have to filter through all the states. If lambda is close to 1, then the learning process doesn't account for the relationship between any of the states. It's just, that will happen somewhat just because of the nature of the approximation, but otherwise it's just looking at the actual end result of an episode. So we can see that it looks like these higher values of lambda are not good. Yeah, and this is only doing it for scramble of 3 again. So I'm sort of looking at this thing that we had graphed earlier. And then honestly, like all of these values of lambda are kind of equally good at that point. So, we can extrapolate a little bit, like whatever optimal learning rate we have here, like 0.0015, Here I've made it a little lower, and we can see, you know, it's about as good as we can do, apparently, for this scramble of 3. And another goal of doing this parameter study is to see if we start making the problem harder. Like here, now this is 4, and this is 5, and this is, we're going to eventually go to 6. And we can see as the success rate starts dropping, especially because we're not training it for additional steps that might be needed as the problem gets harder, we can see if anything changes about, you know, what values of lambda or what. So it seems like, you know, at least like learning rates early on, as we might expect, it's better if they're a little lower. And it seems like um, the values of lambda that are best are a little bit different than before, where now it favors a little bit higher, so a little bit more, a little bit closer to Monte Carlo sampling than the temporal difference method. So yeah, what did I do? Oh yeah, and this is just showing if there's also different types of eligibility traces that you can use. So this is showing uh, a very common trace to use when we have these binary features is this replacing trace. We can see this lambda value of about 0.5 looks actually good for linear approximation. But again, this is only for 10,000 steps. And then this is showing learning when we scramble 4. So now this is a harder problem. And now the success rate we can see is only about 80% for this, even training for 100,000 steps. And then we have also this value of 5. Okay, and now with 5, so we can see, you know, learning happening a little slower. I cut this off a little sooner. We can see, you know, we're still at least getting more than half the time we're reaching a solution. But the idea here is to see, you know, what is the limiting factor? How far can we get by just, you know, progressively training on higher values of n? You know, and clearly we are running into some kind of wall here where now we're at 7, and this, even though we are clearly improving from random, this is still at a pretty low success rate. And yeah, these are the solution rates for different yeah, this is like if you actually sample what the solution rate is for all the different scrambles. So this is if we train on 5, right? We already saw the learning curve for 5 here, about a 60% success rate. So here it matches roughly with this, right? Where 5, we have a little over 60% success rate on 5. And then, you know, very quickly our performance is degrading. So clearly, you know, there are problems here with linear approximation. What we really want to test is just the usefulness of sort of starting at an easy problem and then progressively making it harder and seeing. I mean, the other option is just here, this is just training it on a range of scrambles, and we can see that it is in fact learning this as well. Now we have a mixture of statistics of how well it's doing on different scrambles. But, you know, once we get past 5, if this sort of 60% success rate around 5 seems to be a wall that we're hitting. And we can see that more clearly here. This is if we run the training and we just actually pass the parameters forward. So we sort of make a curriculum of training where we start with a scramble, let's say of 3, and then we go to 4. And we can see actually with the linear method, once we train it at 3, there might be some early learning that occurs at the very beginning of this, but we are flatlining pretty early in the learning process, where by the time we get to 7, we have a pretty low success rate. And it's not improving that much. Now, whenever you have this problem, there are a couple things you might consider. Like, one question is the training process just bad? Like, is there something wrong with the problem setup? Like, if we just threw at it like a very high scramble, the learning rate would probably just be at 0 the whole time, and it wouldn't get anywhere. But the reason for that would be like we shouldn't train it that way. So here we're training it where we have a value function that we know works for a certain set of cubes, and then we're trying to expand its performance range into a slightly harder problem. And we're still running into this wall. And the other problem we could have is that our approximation technique is just not powerful enough to, capture this problem. So that is likely the problem here with linear approximation, is that like right here, I didn't like do anything. I'm using a very simple approximation technique. I would never expect linear approximation to, have much success on this problem. And but we can use the linear technique to verify some of the stuff like the learning rate, or is there any merit in this sort of curriculum approach to learning. Now, from here, there are a few approaches that you could take. I mean, one is, let's just try to use the same learning technique, like the same, DP lambda algorithm, and just try to use a much more powerful approximator. So that is one approach. The other idea might be to augment what we've learned so far here with some kind of search technique, like Monte Carlo tree search, or something that would take this value function that we've learned, and instead of just using it on its own, branching forward, doing some sort of look ahead search, and making go, because we actually know how the problem is structured. Like we can look forward in the cube, and we can try to, get better value estimates. If we look forward, and maybe the value function on its own isn't good enough to see the states that are closer to a solution, but if we actually search forward with it, then we can improve the performance. And actually, doing this sort of forward search does, here I can show, actually, do I have it? I can show it either later or at another meeting, but this is I just took some notes of using a particular approximation function that I had, and looking at, if I do a tree search with a certain depth, and a certain number of simulations, how much do I improve the performance? So when I did this earlier, so here's an example where I have some policy where it only had a 76% success rate on 7 scramble. When I applied the search with 100 simulations, it boosted it up to 94%. So that's a pretty significant improvement. So this is also the idea behind like AlphaGo, AlphaZero, some of those things where once they had a complete learned value function, then you can apply this tree search on it and just boost the performance of whatever algorithm you have. Yeah, there's more details about the tree search. And actually, there's one other thing I want to. There's a question here. You can understand that 8 tiles times 6 is 48, but shouldn't that be 6 to the 8? And that's just for one cube states. The feature vector does need, I mean, can represent all cube states, but the reason why, so there's 48 right unique baselets of the cube, right? So each cube can just be represented with 48 integers, each of which is 1 to 48. So if I represent each of the 48 integers, right, as just 48 length bit vector, then that's where it comes from.
I'm still not understanding that, because each of the facelets can be one of 6 colors. Yes.
Oh no, so the colors are totally irrelevant, because here, once I number them 1 to 48, they're all unique pieces. You can forget about the colors.
But I'm take a step back. Where are you getting that 48 from? You're multiplying 8 times
No.
6. Yes.
Yeah. Hmm.
Okay. So each of the facelets can be one of 6 colors.
No, because actually each facelet is unique. Like, so if I look at the solved cube, like this one, right?
Uh-huh.
This facelet is actually, there's only one piece
Oh,
here
it's an
where the top
identity.
is, yeah.
Are
So
you saying that's an identity?
I'm always comparing the index with the position in the solved cube. So, right, if I number all of them in the solved cube,
Okay.
they're
I
all
got it.
unique
I got it.
Okay.
Okay, thanks.
Yeah, sure. Okay. So actually there's, I think going into all the nonlinear approximation is probably going to be too much to handle now. And you know, the success. I could show some of the, so if you do like more powerful nonlinear approximation and you scale up the size of the network, I'm trying to actually see how the scaling works a little bit better, but you can end up doing a lot better. Let me just see if I can show a little preview of, oh yeah, so this is showing like after a bunch of other steps that I haven't talked about yet. This is like if I scramble the cube 13 times and I have a much more powerful approximation technique that I trained differently. Even this cube actually, the vanilla policy was unable to solve it. It's a little outside of the range where it has a very high degree of success. But applying just a little bit of forward search even to that makes it so even with this amount of scramble, it can actually solve the cube. And actually, if I run this again, it doesn't solve it every time. Yeah. So what this is showing here is that the policy that I ended up training through all these other techniques didn't succeed in solving this cube, but pretty frequently. Now, this tree search actually isn't even doing a very fancy tree search because the way I've set this up, it's only doing a depth of 1. So effectively, all I'm doing here is doing a 1-step look ahead on the policy that I've trained. But even that does boost the success a lot. You can collect statistics on it and see. But before, maybe one thing to add to this is just another technique which we're not going to actually end up using to succeed at this problem, but which is an interesting idea that I think most people, when they hear about this cube, like think of this, which is, well, what if we just try to go backwards? So what if we take a cube and just scramble it, let's say like 20 moves, right? We end up with a scrambled cube. Now, we know how to solve that cube, right? We would just reverse every move. So we can actually generate an infinite amount of examples of solving a scrambled cube in that way. And one idea we might have is, okay, let's just keep generating data like that. And then we know for each of the states we visit along that trajectory what the value should be, right? We can just use like Monte Carlo sampling to look at, we know exactly how many steps it is away from a solution. Then we can try to learn a value function with however, elaborate of an approximation technique we want on that data. And then we can use that value function to compute an optimal policy. So we can try to so in this way, we're not really trying to learn how to solve a cube. We're just seeing examples of the cube being solved. And then it's much more similar to supervised learning you would find than, because we're not actually doing any like policy improvement in this case. So anyway, it sounds like a really good idea. I don't know if anyone's thought about this problem, if that occurred to them, but can anyone think of a reason why this technique might not work very well? I can show a little bit how you would set up the problem in this way. But here, this is just starting with a solved cube and scrambling it, collecting the trajectory of that scramble, right? So here's an example of one of these trajectories. So we scramble it for 30 moves. So we have the cube solved. So now here are the moves. We can reverse all these moves and go from scrambled cube to the solved cube. Now, one question is like, how do we actually apply these techniques with this problem setup, which is a little bit, foreign to how we would normally set up a problem? So there is one trick that we can use. Oh yeah, so here, yeah, so this is just an example of, I can make this policy that unscrambles the cube. This policy is not a real policy because it only works on the states that were visited along this scramble path. So as long as I don't deviate from that path, I know how to unscramble the cube. And that's what's being shown here. This is the one I had earlier with these, an example where the cube starts scrambled, and then at the bottom, this is, you could see just one move away from being unscrambled. So one thing I can do to make this problem work is I can actually effectively save the whole trajectory of how to unscramble the cube within the state. So what this does is it initializes what I'm calling a reversible cube. But what it's doing is it's scrambling it, and then it's generating this lookup table of how to unscramble it. And it's saving that in the state. Now, this will not be visible to whatever approximation function I have. So I will hide this information from when I'm trying to learn. But when it comes to generating the data, this will allow me to use this MDP with this like special policy. And what I'm trying to learn is this policy. So this is like hidden, but all it will see is actually what this policy is doing, the actions that are taken. But the goal is like to learn whatever this thing is doing. Okay, so scramble it, I make the problem reversible with this little trick, right? I always have of course, this only works for that scramble state. So this only works because I'm staying on that path. Like I get to a scramble state, and then the policy I'm following is always going to reverse that in the precise way that it knows how to reverse it from the original scramble. So now I can just use a Monte Carlo technique to directly try to learn this value function. And this is just showing linear approximation on this. Here to make, again, like to sort of test this technique, I'm only doing it for 5 moves. So here, this is just making this reversible problem only to a depth of 5. We already know that 5 scrambles is fairly solvable. We can get a very high success rate on it. So now we're doing what this is supposed to be doing is learning the value function of this special policy. And right, it's doing it for a lot of steps. Like every time we do this, we generate a new episode. So this is not, it's sort of like, it's not really going to overfit because essentially we have an infinite amount of data we can keep generating. And this is showing just the error function. So clearly like it has learned some kind of value function for this policy. Now, if I actually test this, like collect statistics on this. So now what I'm doing here is evaluating this, what appears to be this policy that I've learned. Where now like I have sort of the synthetic policy I've made by cheating. And now I'm trying to learn an approximate version of the policy. And we can see that even though it appears like we've learned this with a very low degree of error, we're still failing quite a bit on just 5 scrambles. And even like 4 and 3 doesn't have a 100% success rate. And even if here I'm doing it now with nonlinear approximation. So I have a much more powerful approximator I'm using. I have like 256 neurons, 5 layers. I try to train this. This could probably train for more steps. And then when I evaluate this, I have the same kind of, like, the success is okay, but for what appears like all we're seeing is examples of a 5 cube being unscrambled, like perfectly every time. And even after learning it, we appear to not have a very high degree of success here. Right, here's doing it with TD learning, where again, we're like learning it what appears to be very well. And then we can see again, like, okay, it's decent, but not great. Again, with a neural network, it's like, well, this is even worse. This may be actually due to an overfitting problem. So, there's a question here of like, what is actually going on here? Like, we appear to be successfully learning this way to like unscramble a cube, which has been scrambled 5 times. But then, somehow like the technique isn't actually succeeding that well. Like it should be doing much better than it is. So this is kind of like, if you're trying to like, reverse, like you want to learn how to put something back together. So you have a video of someone breaking it and then you reverse the film, in theory, it's like that's a way to reconstruct it. But like somehow this reversal we've done is not, learning the most useful thing. So remember how, so I had generated this scramble trajectory here, right, for like a bunch of moves. Now, because I have the tabular solution that I already learned, I can at least see if any of these scramble cubes are within that tabular solution, which the ones close to a solution will be, then I can see what they look like in the tabular solution. So this is showing like on the way for the cube being unscrambled, what the value is. And then all these NAs just represent, like now it's outside of that range of states. Okay, and if I do this, actually, will this, no, it's gonna be the same. I have to generate the trajectory again. Here. Okay, so every time I click this, it'll regenerate this trajectory. And then it will show what those states look like. Now, sometimes we actually get this really nice progressive increase in scramble. So this is 1, 2, 3, 4, 5, 6, 7. So that means that the first 7 moves, if we look at just from here to here, every scramble move that was made, if we reverse it, is actually the optimal path to unscrambling the cube. So if we just look at this one example, it looks like learning this, whatever policy did this, at least over this range, would be what we want to learn, like the correct thing. Now, if I keep generating this though, like let's look at this one. So what this means is that on the 3rd scramble step, right, this was only 1 step away from being solved, and then we made backwards progress, and then we're back to here again, and this is 2, 3, 4. And if I keep generating this, you'll see here like 4, 3, 4, 3, 2, 1. Now remember, in order for this technique to work, for the value function we learn to be any good, we have to actually learn like real like progress towards solving the cube. Like each step we make has to make sense. And our approximation function has to actually learn like the patterns that exist in the relationship between those cubes. But, it appears as though like doing this reversal is not actually producing anything that we can learn from. Like if you as a person, saw like this out to 30 moves, like the way in which this reversal policy is unscrambling the cube is not the way that we would actually want any real policy to learn how to do this. Like it's not based on any sort of pattern or analysis. It's much more random than that. And it is just like a complete fluke trajectory that, maybe if we were lucky, there would be, I mean, there clearly is something to learn from it, but it's clear that if we go out to these higher degrees of scramble, that, it's not actually going to Um, when we reverse, sorry, I don't quite understand your question about the neural network, but all these examples I showed were of actually either learning with Monte Carlo or with TD learning a function which is basically approximating whatever this reversal is doing. And the point is that there is no, like we want to be able to generalize. Like if we see a particular trajectory of states, we want to generalize that to a solution that works on any random states that we encounter. And the problem is that this like reversal technique, it's really bad at producing general results, because especially as we get farther out in the scramble process, like these moves, like the hardest part of the problem, like we can actually learn an exact solution here, and then with other techniques, even without that much work, we can extend this to very high success rate, even out to like 10, 11 moves. The really hard part of the problem that we need to solve is figuring out, how do we distinguish a state which is like 20 moves from being solved to one that's 19 moves from being solved, and learning how to make progress in that range, which is much farther away from the solution. And if we look here at just like how even close to a solution, we're sort of teetering back and forth between things like we're not making uniform progress to solving the cube. And that problem's only going to get worse as we go out here. And even if we have really good function approximation, every time we look at it, there's just nothing general to learn from this, which is not right. It's not too surprising, but the basic problem is that unscrambling the cube by reversing it, right, that trajectory won't look anything like the trajectory of someone or some algorithm which is actually solving the cube in in a repeatable way. Like nothing about this reversal is going to be repeatable. It's just going to be a fluke of this randomness. So we can try to look ahead, but like unfortunately this idea doesn't pan out too well. Yeah, you could try it with a little bit harder stuff or more scrambles, but I think just the idea itself is too flawed to have any hope of working, because yeah, it's just like too lucky that like we're just sort of searching around in this random space of 43 quintillion cubes, and seeing that one magic path, it's really just a coincidence, like that sequence that ends up reversing it. So yeah, I think if we go on or do continue with this problem next time, we can start looking at some of the more powerful nonlinear approximation techniques that do much better. Yeah, I showed some of the, let's see, some of these results, but yeah, this is an example of some of the statistics for training this a little more. Yeah, so for this particular, so this is like using the same state representation, but with a nonlinear approximation. This is just a fully connected network with it's still not a very big network, just 128 layer size for each layer. We can see after this amount of training through a sequence of moves that now even at like 8 script, it's like 95% success rate at 8, and then even at 10 it's 75. And now we're actually getting into the range where even though when we get to, let's say, 12, it only has a 50% success rate, we can start, we could either extend the training even more, and maybe with a longer time training, it would have more success. Or we can start enhancing it with some of these forward search methods like this Monte Carlo tree search I showed earlier, right? Like this, where now, we like take a technique which maybe can't quite solve this cube, and now suddenly it can. And the next step beyond this is maybe using this forward search to then further improve the value function, which is sort of like what happens in like AlphaGo style algorithms where, but there's also other ways to use this forward search within the training process itself, which we could also talk about a little bit next time. So yeah, depending on what happens, I mean, I might make more progress with the problem and actually be able to solve much higher scrambles. But yeah, there is more. The main thing I didn't go over here was how to extending this to the nonlinear techniques. And then there's also another idea of modifying the MDP itself to so that more of this look ahead and the number of moves actually occurs within the step function of the problem itself. But I guess, yeah, we'll save some of that for next time, or move on to a different problem.